All right, guys, lesson 2.2. Now, I keep going into these videos like, okay, this next one's going to be a little bit faster. And then it doesn't end up being faster. And same with lesson 2.2. This one's going to be a little bit faster. I already know that's not going to happen. We're going to cover a lot of things in this video. And the truth about calculus is it's hard to record a video and not actually have a discussion with you guys. It's hard to not have that back and forth and make sure you're understanding. And it leads to maybe trying to over-explain things sometimes. But when you're at home and you're trying to learn these important concepts that are brand new, maybe that helps out a little bit. Always feel free to, if you get something and you feel like I'm just explaining it more than you need me to, there's a fast forward button. It's pretty cool. All right, so lesson 2.2, derivative rules. Now, we already talked about taking a derivative in 2.1, but today I'm going to give you some shortcuts so you don't have to use that great big limit formula all of the time. You do still need to know how to use that formula. We're going to practice it on a lot of the homeworks because it is going to come up on the test. It's going to ask you to use the limit definition of a derivative to find a derivative. But there are some really cool shortcuts that you can use so that you don't have to use that definition all of the time. We're also going to talk a little bit about tangent lines and the formula for the tangent lines, what it means to be non-differentiable, and retouch a few things on rate of change. So a lot of things to talk about today. First of all, we already mentioned the expression d dx means to differentiate with respect to x. The most common derivative, d dxy, is usually written as dy dx. So if you see something that says like d dx x squared plus 3x, that is saying I want you to differentiate with respect to x. That's all that means, okay? It means take the derivative of this part. So now that that's out of the way, derivative rules. I've got a little sticky note here that I'm not going to go over in the video. It is something that we're going to cover in class, but the first rule is called the power rule. And if you look at this equation right here, it says that the derivative of x raised to some exponent is equal to the exponent gets moved to the front of x, and the new exponent becomes n minus 1. So let me show you what that looks like. So to take the derivative of, let's say, like x to the 5th, the shortcut is I move the 5 to the front, the x goes here, and this becomes a 4. That's it. You don't have to do the big limit formula. You use the shortcut. If I want to take the derivative of x to the -3, that -3 comes to the front, the x stays there, and this becomes -4. So you move the exponent to the front, and you reduce the exponent by 1. All right? Next shortcut. You guys are going to love these. So we're going to make life go a lot faster. The constant rule. If c is a constant, the derivative of a constant is 0. So the derivative of 8 is 0. The derivative of -3/2 is 0. The derivative of any constant all by itself is equal to 0. The next rule, scalar multiple rule. If c is a constant, then the derivative of c multiplied by a function is equal to c multiplied by the derivative. And it makes it look a lot, I don't like this rule because it looks a lot harder than it is. The derivative of, let's say, -8x to the 5th. I have a constant being multiplied by a function x to the 5th. The 5 still gets moved to the front, but it gets multiplied by that -8. So that becomes -40x to the 4th. That's all that means. If there's a constant in front of the function connected to it, then it's going to get multiplied with the derivative. Okay, sum rule. The derivative of f of x plus g of x is equal to f prime plus g prime. So the derivative of x squared, let's do a minus. We haven't done many of those. Oh, maybe we have minus 3x to the third. The derivative of that is 2x minus 9x squared. When you're adding or subtracting them together, you can take derivatives of the different parts and then just combine them. All right, let's practice. Example number 1, f of x equals x to the fourth. So f prime of x, I drop the 4 in front, and the 4 reduces to a 3. Remember how long that took using the limit definition? Now it's a 5-second problem. Number 2, y equals x to the negative 2/3 plus 0. So we're going to do one of these at a time. The x to the negative 2/3, the negative, oh, where'd my pen go? The negative 2/3 goes to the front. The x stays where it is, but I have to minus 1. So to minus 1 from negative 2/3 is going to become negative 5/3. Now that plus 3, don't forget about this plus 3. When I take the derivative of a number 3, I get 0. So plus 0, but of course we don't have to write that. So we can just write negative 2/3 x to the negative 5/3. It's ugly, but it's really fast. Okay, number 3, 5 minus 1 over 2t to the third power. Okay, we got to be careful when these are on the bottom. Here's what you're going to want to do. You're going to want to say, oh, that's 0 minus 1 over 6t squared. And that's not true. So when the exponent is on the bottom, we need to move it to the top. So I need to take this t to the third, and I need to move it to the top. So this actually becomes 5 minus t to the negative 3. And let's put that 1/2. Actually, yeah, let's put the 1/2 is kind of, I mean, we can put it on the bottom, but we'll put it in the front. T to the negative 3. So 5 minus 1/2. The t to the negative 3 gets moved to the t to the third gets moved to the top and becomes a negative 3. Now I can use my exponent rule. I can't use it when it's on the bottom. I have to move it to the top. So the 5 becomes a 0. The negative 3 gets multiplied to the front. So a negative 3 times a negative 1/2 is a positive 3/2. And then I have t. The negative 3 drops to a negative 4. So that would be my answer, or I can rewrite it as 3 on top and 2t to the fourth on the bottom. Either of those answers is going to be accepted. All right, number 4. F of x equals 5 times 2x cubed. Now, you haven't learned what to do when your function is when your x is inside parentheses. So let's get it out of the parentheses first. So I'm going to rewrite this. The 5 is going to stay on top for now. This 3 needs to get distributed to everything. So that becomes 2 cubed x cubed. I know some of you don't need this review, but it maybe has been a while. So f of x equals 5 over 8 x cubed. Now again, the x cubed needs to move to the top. So this becomes 5x to the negative 3, and the 8's on the bottom. Now I can differentiate. Now I know how to do this. So f prime of x equals negative 15 over 8 x to the negative 4. And you can stop right there, or you can rewrite it, which I don't recommend in calculus because you make mistakes when you rewrite things. And they don't expect you to rewrite things. So negative 15 over 8x to the fourth. Either of those is going to be accepted. As long as you rewrite it correctly. You rewrite it wrong, it doesn't matter that you had it right at some point. If you were to simplify that and simplify it wrong, now you got the question incorrect. All right, higher order derivatives. So when you take a derivative, you get another function. So you can repeat the differentiation process. You can take the derivative of a derivative, and you can keep doing that over and over again. That's called higher order derivatives. So the first derivative, I've just got some notation here. The first derivative looks like y prime. That means just take the derivative once. It looks like f prime of x. It looks like dy dx. It looks like take the derivative of f of x. The second derivative looks like y double prime, or f double prime of x, or d squared y over dx squared, which is a little confusing because the squared goes in two different places. That just means take the derivative twice. Third derivative, y triple prime, f triple prime of x, d cubed y over dx cubed. Take the derivative 3 times. As we get into some of the physics and some of the applications of derivatives, these all actually have names. F of x is usually your position function, is the name. That gives us a position of an object. The first derivative gives us the velocity, right? The rate of change of an object. The second derivative gives us what's called the acceleration. The third derivative gives us the jerk. It's kind of like torque. The fourth derivative gives us something called jounce. And from there it keeps going. It actually gets kind of funny because the fifth derivative is called snap. The sixth is called crackle. The seventh is called pop, just like Rice Krispies, snap, crackle, and pop. The seventh and eighth are actually, I think it's lock and, I can't remember what the eighth one is. Something like that. We don't really deal with those, not in this class, okay? We are going to deal with these two a whole bunch. We're going to use the first, second, and sometimes we'll use the third derivative. Not a lot, but sometimes we will use it. Just don't expect to go into snap, crackle, and pop, at least not in this class. So example number 5, for the function f of x equals 1 over 2 cube roots of x squared, find f prime of 1 and f double prime of negative 8. Okay, so it wants me to take the first derivative and then plug a 1 into it. And then it wants me to take the second derivative and plug in a negative 8. So let's start with the first derivative. I can't quite do that yet because first of all, my function's on the bottom of a fraction. You don't know how to do that. So let's clean this up just a little bit. And I'm going to do this step by step. So f of x equals 1 over 2. Now that cube root, we're going to move the cube to the bottom of a fraction. So that cube root is going to become x to the 2/3 power. Now I can't do that still because it's on the bottom. So I'm going to do f of x equals 1/2 x to the negative 2/3. I'm going to move that to the top. Now this is something I can work with. So f prime of x, let's take the derivative, multiply the negative 2/3 to the front. So negative 2/3 times 1/2 is going to be, let's see, the 2's cancel. So that becomes negative 1/3 out in front. X and the negative 2/3 minus 1 becomes negative 5/3, which is not very pretty. That's not a very pretty number right there, right? So let's do f prime of, it wants us to plug in a 1. So negative 1/3 x to the negative, not x, what am I doing? 1 to the negative 5/3. Now 1 to any power is 1. So this one's not too bad because my answer just becomes negative 1/3. Now we got to do the second derivative. Now we've got to do f double prime of x. So I'm going to take the derivative of the derivative. So that negative 5/3 is going to get multiplied to the front. So negative 5/3 times negative 1/3 is a positive 5/9. And I apologize, I didn't space this very good. X, and then I have to minus 1. So negative 8/3. Yikes. Okay, So let's do f double prime of -8. So I've got 5/9 -8 to the -8/3. Okay, here's where we need to have a little discussion, okay? Right now, I'm going to erase this for just a minute because it's bothering me. This is not pretty. And technically, it wants me to find what this value is. Now, here is the wonderful thing about calculus. I can stop right there. If this was on the AP test, I don't have to try to, I have no idea what -8 to the 8th power is. If this was a calculator question, if this was a calculator question, you wouldn't have even done any of this by hand. You would have done the whole problem on the calculator. But if this was a non-calculator question, stop right here. You don't have to actually raise -8 to the 8th power and then take the cube root of that ridiculous number and then multiply it by 5 and divide it by 9. It's never going to ask you to do that much algebra. This is where you stop, right here. Again, if it wanted an exact answer, this would have been a calculator question, and you would have had the answer 5 minutes ago, all right? So this is what we're going to call this right here. I'm done. That is f double prime to the -8. F double prime of -8, not to the -8. That's going to be my answer today. All right, equation of a tangent line. Guys, this is going to come up a lot. We're going to start practicing this on lots of the homework because there are a lot of problems throughout the AP test that want you to get an equation of a tangent line. So since the derivative of a function, since it gives us the slope formula, we can use that derivative to write an equation of a tangent line. All right, so some of that might sound a little bit scary, but remember clear back in, 9th grade, you learned how to write the equation of a line. And the formula that you're going to use, I don't know why it's not here in the notes. You probably need to add this to your notes. The formula is going to be y minus y sub 1 equals the slope of my tangent line multiplied by x minus x1. This right here is your tangent, equation of tangent line. You need to know that. That is one that you absolutely have to memorize. You're going to have to use it on the test, I promise. So before we start talking about the normal tangent, because I'm tempted to just skip it because it doesn't come up very often, let's use this formula for a tangent line. So example 6 says, find an equation of the line tangent to the graph of f of x equals 4x to the 5th minus 3x squared plus 5 at the point 1, 6. Okay, so for the equation of a tangent line, if I look at this equation, I need the slope of the tangent line, and then I need just any point that's on the line. It doesn't matter what point it is. I just need a point. Well, it gave me a point. It doesn't always do that. Sometimes it gives you the x value, and you have to find the y value, but this one gives me a point. So all I need to do is find the slope of the tangent line at that point. Well, you know a really quick way to find the slope. It's to take the derivative. So f prime of x equals 20x to the 4th minus 6x. The plus 5 goes to 0. There's my formula for my tangent line, right? That equals the slope of the tangent. Not my formula for my tangent line, my formula for the slope of my tangent line. Now, I want a specific slope. I want the slope at the point when x equals 1. So this becomes 20 times 1 to the 4th minus 6 times 1, which is just 20 minus 6, so that's 14. So my slope, my tangent line slope at this point is 14. So now I'm going to plug it into the formula. y minus y1. Well, y1 is this value right here, 6. So y minus 6 equals the slope of my tangent, 14, multiplied by x minus x1, which is 1. Again, this is calculus, guys. Stop right there. You don't have to simplify. You're going to want to. I know especially you juniors taking this class, you're going to want to distribute the 14, and then you're going to want to add the 6 to both sides so that y is all by itself. You don't have to do that. This is the formula for the tangent line, the equation for the tangent line. If it was a multiple choice question, it might simplify it. So you do need to know how to simplify it, but you don't have to actually do that on the test to get the point for the right answer. So yeah, if this was a multiple choice and none of the answers looked like that, you might have to distribute the 14 and then move the 6 over so you end up with what? Why isn't this writing? Hello? Uh-oh. Did we freeze? Something's happening. Oh, my pen's getting unscrewed. That's what's happening. Okay, here we go. So this becomes y equals 14x. That's negative 14 plus 6. So that's going to be negative 8. Are we okay with that? Or it might have not distributed. It might have been y equals 14x minus 1 plus 6. All of those are the right answers. Unless it's multiple choice, you don't have to pick a specific one. Just stop up here, okay? All right, number 7. Find an equation of the normal line to the same curve at some point. Okay, so a question did come up last year about the normal line. It wasn't a big question. It was a multiple choice, but it made me feel like if it came up once and a lot of people missed it, then it probably is going to come up again. So I want to at least acknowledge this idea of a normal line. So I put a note up here that the slope of a normal line is the negative of the what do we say? The negative of the tangent line, but you flip it over, right? So if my slope, come on, pen. If my slope of my tangent line was 7, then the slope of my normal line is going to be negative 1 over 7. If the slope of my tangent, if the slope of my tangent was negative 1/4, then the slope of my normal is going to be positive 4. You flip it over, you change the sign, okay? So the equation of the normal line at this same point, I'm still going to use 1/6, but instead of my slope being 14, my slope is going to be negative 1 over 14. So I would get my y minus 6 equal, whoa, I'm like moving way ahead. Y minus 6 equals negative 1 over 14 times x minus 1. I don't anticipate that coming up, but you know that these calculus people like to do that. So just so you know, we're not going to practice the normal line a lot this year, but I want you to be familiar with that. All right, non-differentiability. We mentioned this in the last class, that the derivative does not always exist. There is not always a slope at a point. And here are examples of where a derivative does not exist, okay? A derivative does not exist when there's a hole in the original function. So all of these functions are f of x, okay? If there's a hole in my original function, the derivative does not exist at that point. If there's a jump in my original function, the derivative does not exist at that point. Sorry, that's just my pancreas talking. I should have had that turned off better. A vertical asymptote. There is no slope at a vertical asymptote because there's no point there. If there's a sharp turn, we also call this a cusp. In fact, I'll probably call it a cusp most of the time. If there's a sharp turn, if there is a sharp change in slope, the problem is I can't find a tangent line at a cusp. If I have this point right here at the end, I can draw lots of lines that only touch it in one place. So there is no slope at that point. And if there is a vertical tangent, this one's kind of interesting. And it's hard to spot with the original function sometimes. You'll see this on like cube roots and things, is usually where it comes up in calculus. But if the tangent line goes straight up and down, it doesn't have a slope because technically its slope is infinite, right? There is no slope. So those are where a derivative does not exist. So I want to do a couple problems where we look at the original function and see if we can figure out where the slope does not exist, okay? Before we do that, an important note right here. If a function is not continuous, it's not differentiable, right? If you look at all of these functions, not continuous, not continuous, not continuous, all three of those are not differentiable. So if it's not continuous, it is definitely not differentiable. But look at these two. These last two are continuous. Both of these are continuous, but they're not differentiable, okay? So what that means is that continuous does not imply differentiability. It goes the other way. If it's differentiable, it's definitely continuous, but just because it's continuous does not mean it's guaranteed to be differentiable, okay? And we'll get deeper into that later. My really quick videos at like 4,800 minutes now. Okay, number 8, find where these functions are not differentiable. So when I look at f of x equals the absolute value of x, I hope that what you picture in your mind is this, that v. It is not differentiable because I know there is a cusp. There is a cusp at x equals 0. There is going to be a sharp turn at x equals 0, okay? Number 9, f of x equals a piecewise function, x squared when x is less than or equal to 0, x when x is greater than 0. All right, so to check this one, two things are happening, right? To the left, if this is my function, to the left, something is happening. To the right, something different is happening. What I want to know, first of all, is do they meet at the same point? When my functions meet, do they meet at the same point? Because one function might go here and the other function might be here. It might be a jump discontinuity. So what I'm going to do first, I'm going to plug 0 into both of these. 0 squared equals 0. 0 equals 0. Okay, good. So they meet at the same point. So that means that there's not a jump discontinuity. But remember the sharp point, remember this cusp? We have to check to make sure there's not a cusp at that point. All right, and again, this is one of those things I promise you is going to come up on the test. It's going to give you a piecewise function, and it's going to ask you if it's differentiable or you can find the derivative. The second thing I need to check, I know that they meet. I need to make sure that they don't make a sharp point. And the way that I do that is I find f prime of x. So the top function becomes 2x. The bottom function, the derivative of x, did we talk about this one? I think derivative of x, if you had, technically you have x to the first power, you drop that down to the front, that becomes 1x to the 0. Anything to the 0 power is 1, so the derivative of x is just 1. I can't remember if we mentioned that specifically, but if you do the math, you can figure it out if you forget. Now I'm going to plug 0 into both of these, okay? Because what I want to know, here's what I want to know. To the left of 0, is my slope the same as it is to the right of 0? If it is, I'm going to have a nice smooth transition right there. If my slopes are different, I'm going to have something like this. There's going to be a cusp at that point. So I have to check both. I have to check the value and the slope. So when I plug 0 into 2x, that becomes 0. When I plug 0 into 1, well, I can't, that becomes 1. So what that means is to the left, I have a slope of 0, but to the right, I have a slope of 1. And I guess technically this is actually looking more like this, right? So that point right there is a cusp at x equals 0. So remember to check the derivative at the point and the point. Okay, let's do that again on number 10. We're going to plug 0 into both of these. So 0 squared equals 0. 0 squared plus 1 equals 1. So those two don't even meet at the same point. So there is a jump at x equals 0. There's a jump discontinuity. So it's not continuous, or it's not differentiable. Number 11, f of x equals x over x times x minus 1. Oh, geez, lots of problems with this one. Remember, if I were doing a limit, these would cross out. Those would cancel. What did we call that? We called that a hole. We called that a removable discontinuity when x equals 0. So on my function, there's a hole at x equals 0. And not only that, look what's left over, x minus 1. So there's also a vertical asymptote when x equals 1. So this one is definitely not differentiable because there's a hole and a vertical asymptote. That's a messy function. Okay, number 12. F of x equals the cube root of x. Okay, I'm going to warn you with cubes. Please, please, please check the derivative and check the function, okay? Because here's what happens. The cube root of x, I can plug 0 in. The cube root of 0 is just 0. No big deal. There's nothing wrong with that. But look at what happens. If I take the derivative, well, sorry, first I've got to rewrite this. F of x equals x to the 1/3. If I take the derivative of that, I get 1/3 x to the negative 2/3, and that equals 1 over 3 cube roots of x squared. So there's my slope formula. Do you see a problem if I were to plug a number into that slope formula? I'm going to end up with a 0 on the bottom. If I plug 0 in, if 0 was my x value, my bottom is going to become 1 over 0. That is bad. So what that means is at the point x equals 0, I don't have a slope. Well, technically I have a slope. It's going to be straight up and down. So I have a vertical tangent at x equals 0. And if you think about the x cubed function, right? We have this thing right here. So right there, my slope goes straight up and down. That's a problem. We don't like that. Okay, let's move on. You'll get plenty of chances to practice those. Rate of change. Remember the method of finding, we had the average rate of change, and we've done these a lot, where you use your old slope formula. Now we can use differentiation to find the instantaneous rate of change. So the instantaneous rate of change, remember, is just the derivative. We can use that derivative tricks and shortcuts that we know. So for example, if f of x equals x cubed plus 2x, find the average rate of change. Oh geez, from x equals 10 to x equals 30. Okay, average rate of change, that's my slope formula. Okay, y2 minus y1 over x2 minus x1. So my average rate of change is going to equal, I got to do some math first. I've got my x values, but I need a y value. So f of 10 is equal to 10 cubed plus 2 times 10. 10 cubed is 1,000 plus 20, so that's going to be 1,020. You okay with that? Well, I'm moving on anyway. F of 30, 30 equals 30 cubed plus 2 times 30. 30 cubed is going to be what? 27 with 3 zeros, 27,000. This is 60, so that becomes 27060. Wow. So my points are 10, 1020 and 30, 27060. Yuck. So now I can plug those into my slope formula. So 27060 minus 1020 over 30 minus 10. So that becomes, what? 26040 over 20. The zeros are going to cancel. That's going to get cut in half, so 1302. So my average rate of change is 1,302. That's my average rate of change between those 2 points. Number 14 wants me to find the instantaneous rate of change. That means f prime of x. Cool, I know a shortcut. X cubed becomes 3x squared. 2x becomes 2. Because x, remember, x just turns into a 1. 2 times 1 is 2. So f prime of x equals 3x squared plus 2. All right, so f prime of 10, 3 times 10 squared plus 2, that's 100. 300, that's 302. So my instantaneous rate of change is 302. My average rate of change, and I guess that's not, maybe it should have used x equals 20 instead of x equals 10 to kind of find the middle ground there. But at 10, when x equals 10, my rate of change is 302. By the time I get to 30, my average has been 1,302. So, all right, homework. Here's what I need you to do. So the homework, does that look like the word homework? For 2.2, I want you to do all real numbers, except there was one that I did not want you to do. I don't want you to do, it was down here somewhere. What did I not? Oh, 47. Don't worry about 47. So all real numbers, but not 47. That make you excited that you get to go all the way through 46 questions and then you get to skip one? I know, it's because I care about you. Good luck.